Okay, part 3 of chapter 9, center of mass. The center of mass is a point that represents the average location of the total mass of the system. Suppose that you have a system of n particles or n objects. You can think that they are all one particle and the mass of all of them is located at the center of the mass. So in here, I have two particles, m1 located at x1 and m2 located at x2, okay? The center of the mass will be closer to the heavier one, so by looking at it, I can tell that m2 is greater than m1, okay? And in order to find the center of mass, we have an equation like this, m1x1 plus m2x2 over m1 plus m2. In other words, I can write it like this. Sigma m, the sum of all the masses that are involved in forming our system, sigma m I xi, okay? And here is mi. So I goes from 1 to whatever number that we have for the number of particles in our system. For example, m1 x1, m2 x2, m3 x3, m4 x4, you can all add them up right there. In this case, we have only 2 particles, so it goes all the way to 2. So if you have like n particles, it can go all the way to n. All right. Now, so in general, they shouldn't be located in the x direction. They could be have a value of x and y. In other words, they could have r value. So m1 r1, m2 r2, m3 r3, and so on. And the total of masses will be in a denominator. So if you remember, the r was xi plus yj, and that would be your vector r. So a position of a particle in a system could have a x value and could have a y value associated with it. So it is the mass weighted average position of the particles when we're talking about the center of the mass. For solid bodies, the sum are represented by integrals. So if I have a sphere and I want to find where the center of the mass is, these particles are very tightly close to one another. Or in other words, we have a solid body of enormous number of particles. So rather than having a sum here, I would have an integral here. So r of the center of the mass for a solid body would be the integral of m dot dr, okay? Or in other words, I can write it like this. From 0 to r, whatever it is, from position of 0 to r. This depends on the problem, okay, and where you put your coordinate. And I have the total mass here, m total, or 1 over m, the integral of m dot dr. Okay, but in this case, we're not dealing, with, this could get a lot complicated, but generally for particles of the system, if they are the objects in the system, if they are an individual particles or objects, then we consider them as a sum. Okay, so for the solid particles, as I said, the solid objects, we pretty much can guess where the center of mass is. And for example, for a cube, it will be at the center. For the sphere, it would be at the center. For the cylinder, it would be at the center. For a disk, we'll have the center of mass located at the center of the disk. For a donut, it will be again at the center. Even though there is no particle at the center here, or this part is empty, but the center of the mass of this object will be located at the center. In other words, I can consider this donut-shaped ring, or this ring, to be one particle located at the center with the total mass concentrated on that point. Okay? So it's much easier to find the center of mass for this symmetric object. Okay? Now let's take a look at this, center of the mass. The yellow block and the red rod are joined together. Each object is uniform density, so everything else, so all the objects are uniformly distributed along each object. the center of the mass of the combined object is at the position shown within X, okay? Which has the greater mass, the yellow block or the red rod? Okay, let's take a look. I can say that I have a block, and I can consider that all the masses of the block being located at the center. So this is the center of the mass of the block, okay? And I can consider all the masses of this rod being located at the center of the rod. So center of the mass of the rod is right there. Now, if you're comparing, you can kind of tell that the center of mass of the both objects is much closer to the heavier, as I said. Remember this? I said that the heavier object, the center of the mass will be closer to the heavier object, so M2 is greater than M1. I can use the same analogy here and say the center of mass, which is right there in the X, is closer to the block than to the rod. So the yellow block is heavier. Okay. Now, velocity of the center of mass and momentum. So let's say that I have two particles in my system, and I can find where the center of mass is. And the center of mass location, the X of the center of mass is M1 X1 plus M2 X2 plus M1 plus, over M1 plus M2. I can find where it's at. But if the objects are moving with a velocity of M1 and M2, then I can find the velocity of the center of mass, because center of mass is also moving, okay? If particle 1 moves to here and particle 2 moves to here, delta x1 and delta x2 with the different velocities, m1 and m2, then I can find the velocity of center of mass, okay? So in other words, I can write, instead of the delta x, instead of having x at the center of mass here, I'll have delta x of the center of mass. M1 is the same, delta x1 plus M2, delta x2, M1 plus M2. If you divide everything by t, so I'm dividing everything by delta t, then I would have delta x center of mass over delta t being equal to M1 delta x1 over delta t plus M2 delta x2 over delta t divided by M1 plus M2, which means the velocity of the center of mass is M1 velocity of 1 plus M2 velocity of 2 over M1 plus M2. And these are vectors, so I am putting an arrow on top of every one. So this is important. Now, so the total momentum is equal to the momentum of the center of mass. In other words, I have multiple objects. I can consider those multiple objects being concentrated at the center of mass. And so the total momentum is equal to the momentum of the center of mass. All right? If there is no external force, the total momentum is constant. Okay? So total momentum of P total is M1 V1 plus M2 V2 plus so on and so forth, which is equal to M total time V of the center of mass. Okay? So, motion of center of mass. So the total momentum of the system is equal to the total mass times the velocity of the center of mass, as I just said. Total mass times the velocity of the center of mass would be the total momentum of the system. Okay, this is also very important. So I'm going to highlight it because I like doing that. Okay. Now, the center of the mass of this wrench at the right moves as though all the masses were concentrated at that point. A center of mass, a ring-shaped object, or a donut, will move as if it is one particle at the center with all the mass located at that point. So the total momentum would be the total mass times the velocity of the center of mass. Okay? Let's take a look at this. Suppose two ice skaters initially at rest, so the initial velocity is 0 of the system, okay? Push off of one another, okay? If the mass of the man is 88 kilograms and the final velocity and his final speed, I mean, it has some negative here, so it means it's to the negative direction. So its final velocity is negative 1.5 meters per second. And the mass of the woman is 53.9 kilograms, and her final speed is, or velocity is positive 2.45 meters per second. What's the velocity of the center of the mass? It's very easy to calculate. So the velocity of the center of mass, if you remember, was m1 v1 plus m2 v2 over m1 plus m2. Okay? So m1 is 88 times v1, which is negative 1.5, plus 53.9 times 2.45 positive over m1 plus m2. m1 is 88 plus m2 is 53.9. Okay, so you got to put this in the calculator to find it, but it will have its positive or negative sign associated with it. So if this value is greater, then the total, everything will be negative. But if this is less than that, if this 88 times negative 1.5 is less than 53.9 times 2.45, then everything will be positive. So whatever it is, put it in the calculator to find it. External force and the center of mass. So if the net external force is not 0, if the net external force is not 0, so what would happen if it was 0? If the net is 0, then delta P is 0. Okay? But if the net external is not 0, so that's, I have to put a den here, because if you're reading only the file, you wouldn't be able to understand it. So, but in our case, if the net external force is not 0, the total momentum is not conserved, and the velocity of the center of mass changes. Okay, so if the F net is not 0, then delta P is not conserved. The delta P is not 0, so that means P2 is not equal to P1. Okay, so the velocity of the center of mass will not be conserved, because mass is the same, but the velocity would change because the momentum is not equal finally and initially. Okay, so when I'm writing sigma F equals ma, or when I'm writing F of net equals ma, okay, or F of external equals ma, in all of these formulas, A is A of center of mass. Okay, so sigma F external is m times the acceleration of center of mass. Okay, and this is also very important. So the center of mass moves as though all the mass were concentrated at that point, and it were acted on by a net force equal to the sum of the external forces on the system. So as you can see, sum of the external forces of the system is equals to m total mass times the acceleration of the center of mass. System with changing mass. If the mass of the system is changed, it's one of the areas in physics very popular, or in areas like rocket propulsion. So if a mass of fuel delta m is ejected from a rocket with velocity, with the speed of v, with a velocity of v, the change in momentum of a rocket is delta p equals delta m times velocity. Okay, remember p was mv. Okay, if velocity changes, the momentum will change. If mass changes, the momentum will change. So delta p could be m delta v for constant mass, and delta p could be delta m times v for constant speed. Okay, so if you want to find the thrust of the force in a rocket, F would be delta p over delta p over delta t, and that delta p, which is right here, is delta mv. Okay, delta mv, and I have it right there. And delta m over delta t would be the rate of the change in mass of a rocket, for example. Okay, so this is end of chapter 9. If you have any questions, let me know in the comments. End of chapter 9 and end of part 3 of chapter 9. So let me know if you have any questions.